Last time I briefly introduced this idea of an addition reaction it's called. So again, technically we're going to be looking at what's called an electrophilic addition reaction, where an electrophile is an electron-loving species. So typically we're looking at something that has, say, a region of partial positive charge, where electrons are attracted to that region of partial positive charge in the molecule. And so in an addition reaction, as the name implies, we are adding atoms to an alkene. And specifically, this reaction occurs at the double bond. So we're going to look at the carbons that are double bonded to each other, and we're going to add atoms from a binary substance. We'll look at some different examples. We'll start off with a halogen, a diatomic molecule, where one atom from that binary substance goes to one carbon, that's a double bonded, and then the other atom goes to the other carbon that is or was double bonded. And so we're always adding substances across the double bond to carbons that are adjacent to each other. And so I introduce the example with chlorine. We can do that again. That's fine. Your book actually makes mention of the use of bromine. Bromine is a very common test for the presence of alkenes. So bromine, as you recall, is a brown liquid. And so if you were to add bromine to an alkene, you would make the di-substituted halogenoalkane. And so what would happen then is, because the bromine reacts, the color would change from brown to colorless. Also, it's important to understand that during these reactions, saturation increases. So we're taking an unsaturated compound, an alkene, has a double bond, and turning that into an alkane. Again, the term there is technically, in this case, adding a halogen, we end up with a dihalogenoalkane. And so we're adding, both atoms of that diatomic molecule to our alkene, which then will become an alkane. So I'm going to start off with the equation. So again, I made mention that there's a couple different ways we can write the chemical equation. Usually the equation involves using chemical formulas, and so I'll do that here. Actually, I'll do a couple different ways. So let's say we have ethene that reacts with chlorine. And so again, we have, as we'll see in a little bit, double bond between carbon atoms. That's an unsaturated hydrocarbon. And what we end up with is, again, the dihalogenoalkane. So we have C2H4, Cl2. Now, the chemical equation doesn't really show us exactly what's going on here, such as like, okay, we have two chlorines. Where are they? Is this 1,1 dichloroethane, or is this 1,2 dichloroethane? So where we can really see what's happening is with the mechanism. And so as you recall, when we talked about kinetics, a mechanism shows the steps that take place during a chemical reaction. Now, an organic mechanism, a mechanism for an organic reaction, is quite a bit different than the mechanism for an inorganic reaction. And so in our mechanisms, we're going to use structural formulas. So this is why being able to draw structural formulas is really important. So let's go ahead and draw the structural formula for ethene. And then in close proximity, I will draw the structural formula for chlorine. So let me go ahead and do that now. All right, so here's what we have. So I've taken the structural formula for ethene, and just to save some space here, I'm leaving the H's off just so we can more clearly see what's going on. And I got a little bit of limited space here, but I'll try to squeeze things in so you can clearly see what's going on. Now, before I dive into the mechanism, something that we need to consider is this molecule chlorine. Now, chlorine is a nonpolar molecule. However, the shared electrons are moving around. They move from side to side, and we create that instantaneous dipole that we talked about when we talked about the formation of dispersion forces between chlorine molecules. And so because the electrons are moving from side to side, let's say that this end, the left chlorine end of the bond, develops a partial positive charge. Let's say the electrons are more on the right side of the molecule, so the left side is going to be partially positive, and the right side is partially negative. Well, this region of partial positive charge is susceptible to attack from electrons, hence this chlorine molecule being an electrophile. And so to show the electrons from the alkene attacking, so to speak, the chlorine molecule, we're going to use a curly arrow. So this top line here represents the electrons of the pi bond. And so I'm going to draw, we always start at the location of where the electrons are, and we draw to where those electrons end up. So that pair of electrons will be used to make a bond between the carbon on the left and this chlorine on the left. And it just so happens then that these electrons here between the chlorine atoms are going to go to the chlorine on the right. So this kind of occurs in steps. So what happens? What do we make at this point? Let's go ahead and draw that out. Now, why did I put that plus there on top of the carbon? Well, this carbon on the right has lost a pair of electrons. So it develops a positive charge. And so that positive charge then is susceptible to attack from something that has a negative charge, namely the second chlorine that came from our chlorine molecule. So this electron pair here is going to go to carbon, and that electron pair will be used to make a bond to the carbon on the right. And we end up then with our dihalogenoalkane. In this case, 1,2-dichloroethane. So now maybe you can see why writing the formula as C2H4Cl2 doesn't really give us a good idea of what's going on here. Your book will write something like this: CH2. Whoops, your book uses bromine, so we use chlorine here in our example. CH2Cl, CH2Cl to show that the chlorines are bonded to different carbons. So this is a typical mechanism for an addition reaction, electrophilic addition reaction. This time we're adding a halogen to an alkene. And again, it doesn't have to be ethene. It could be propene. It could be butene. It could be cyclohexene. Doesn't matter. This type of reaction occurs with any alkene. That does, of course, does not include the benzene. As we mentioned in previous lesson, benzene is really not a triene. The electrons in those three double bonds are delocalized, not truly an alkene, so to speak. So, but other alkenes, this reaction does occur. So one more time, we have an instantaneous dipole with this halogen molecule. So let's say chlorine on the left has a partial positive charge. Let's see, I just erased something that wasn't supposed to. And so it makes it susceptible to attack from these electrons here. So the electrons that make up the pi bond are used to form a covalent bond between carbon on the left and chlorine on the left. The electrons here in this bond, again, I'm writing stuff I'm not supposed to be writing. I don't know why it's doing that. Whoops, that went way too far. There we go. Let's try that again. Electrons of the bond between chlorines go to chlorine on the right, making chloride a negative ion. And if we go to this next step here, we see that this carbon is now electron deficient because the pair of electrons that it was sharing, the second pair of electrons it was sharing with the carbon on the left, has now been used to make a bond with chlorine. And so then this electron pair, there's 4 pairs of electrons on the chloride ion. We just need to show one of those pairs, whichever pair is being used to make the covalent bond. So we show that bonding, that pair of electrons uh, forming a bond between carbons, and we end up with our product, once again, 1,2-dichloroethane. Next up, let's look at the addition reaction between an alkene and this time a hydrogen halide. So this could be HF, HCl, HBr, or HI. So we'll just do our example here with HCl. Now let's start this time with looking at the structure of this molecule. So this is a permanent dipole, unlike our last example where we had an instantaneous dipole. And so chlorine being more electronegative than hydrogen, the chlorine end of the bond is partially negative, and the hydrogen end of the bond is partially positive. Again, making it susceptible to attack from an electron pair. So let's again start with the overall equation. So we'll use ethene as our example once again. In this addition reaction, we produce the monohalogenoalkane. Something like that. So chloroethane would be our product. So once again, we see an increase in saturation. We're going from an alkene to an alkane. All right, so let's take a look at the mechanism. Let me draw the structural formulas for both ethene and hydrogen chloride. So your book sort of does this. I like to put the substances in close proximity to each other. I don't want you drawing an arrow from here all the way to over there, something like that. And so we want to put them close together so we can clearly show what's going on. So I drew this in a different color to emphasize this hydrogen here versus the other 4 hydrogens already part of ethene. So again, we have attack. It's kind of hard to draw when your board's not working right. So let's try that again. So electrons go from here. Whoa, this is really not working. There we go. Electrons go from there to there. These electrons go from here to here. And again, we get something similar to what we had before. So hydrogen from HCl is added to the carbon on the left. We form our positive carbon atom here in this molecule. By the way, this carbon has a really cool name. So when a carbon atom loses a pair of electrons, like in this case, because that pair of electrons is now being used as a covalent bond between the other carbon and hydrogen, you form something called a carbocation. So this carbocation, as we saw in the other example, is susceptible to attack from something that has a negative charge, in this case, the chlorine. So, and again, really it's the electrons here going to carbon. So I know it doesn't really clearly look like the arrow's pointing to the carbon, but it's going to the carbon, and you get your product, which looks like this. And again, just for emphasis, I'll show in different colors, that and that. So we end up with chloroethane as our product.